For the next few minutes, imagine yourself traveling 2.5 billion years into Earth's past. Using geological evidence, we have reconstructed what this ancient world may have looked like. No exact map survives. Its coastlines, continents, storms, and colors can only be scientifically interpreted. But this much is certain. Earth was already ancient and it looked almost nothing like home. Across its ocean-dominated surface, immense storms moved above scattered fragments of the earliest continental crust. Beneath the cloud deck, rugged volcanic coastlines emerged from dark seas surrounding the ancient land. Lightning flashed inside towering storms, while wind and rain attacked bare volcanic rock with no soil to protect it. There were no forests, grasslands, or animals, only rock, water, air, volcanic gases, and microbial life. Erosion carved the barren terrain, while volcanism repeatedly rebuilt coastlines from fresh basalt and ash. Lava entered the sea, producing towering steam clouds along shores that must have seemed violently alien. Fresh eruptions continued reshaping the same coast, but the most important revolution was already unfolding offshore. Where hot basalt met cold seawater, minerals entered the ocean and new shallow habitats formed nearby. Along the wave-washed shore, rainwater collected, crossed the black rock, and drained back toward the sea. Those streams carried dissolved elements and fine mineral grains from the volcanic land into coastal water. Beyond the surf, broad sunlit shelves offered stable, shallow environments where microbial communities could spread. Beneath the surface, low, rounded structures rose from the mineral-rich seafloor, unlike anything on modern reefs. These were stromatolites, layered structures built gradually as microbial films trapped sediment and altered their surroundings. Viewed from above, entire coastal shelves may have resembled patterned landscapes made from living stone. Dropping beneath the surface reveals the true builders' thin microbial communities coating each mound and the surrounding rock. Among these communities were organisms capable of oxygenic photosynthesis, the chemistry later inherited by algae and plants. Oxygen emerged as a waste product, gathering into tiny bubbles that detached from the microbial surface. But at first, almost none of this oxygen accumulated in the atmosphere above the ocean. The surrounding water contained abundant reduced iron and other chemicals ready to consume oxygen almost immediately. Submarine volcanism and hydrothermal circulation continually supplied more iron and reactive material to the ancient oceans. When newly produced oxygen met iron-rich water, the iron oxidized and reddish minerals began to form. Those particles settled slowly onto the seafloor, building thin deposits across immense spans of geological time. Later became banded iron formations, the spectacular striped rocks that preserve evidence of ancient ocean chemistry. Their history is complicated. Individual bands do not necessarily represent one simple season or pulse of oxygen. Near productive microbial shelves, small, oxygen-rich oases could exist while deeper offshore water remained largely anoxic. These oases were isolated islands of change inside a vastly larger ocean that still contained little oxygen. Life kept producing oxygen, while oceans, rocks, volcanic gases, and the crust kept removing it. That creates the central mystery. Oxygenic microbes existed early, so why did oxygen finally remain in the air? The answer was not simply that more microbes appeared. Oxygen production had likely begun long before the Great Transition. As productive shelves expanded, the balance between oxygen sources and the planet's many chemical sinks slowly changed. Volcanic and metamorphic gases could react with oxygen, destroying it before any lasting atmospheric buildup occurred. Weathering of fresh rock and chemical reactions in seawater consumed still more of the oxygen being released. Yet, when organic carbon was buried instead of decomposed, some oxygen could remain behind in the environment. Before permanent oxygenation, brief local or atmospheric whiffs of oxygen may have appeared and then vanished again. Ancient sulfur isotope patterns provide a crucial clue. A distinctive atmospheric signature disappears as oxygen becomes persistent. Around 2.45 to 2.4 billion years ago, Earth crossed a threshold now called the Great Oxidation Event. Changing continents, nutrient supplies, biological productivity, volcanism, and climate may all have helped shift the balance. Scientists still debate which combination mattered most, how quickly it happened, and whether every ocean responded alike. Once the threshold was crossed, atmospheric chemistry changed permanently, even though oxygen remained far below modern levels. The transition was uneven. Oxygen probably advanced, retreated, and advanced again while anoxic waters persisted in many regions. Earth had entered a new chemical state, but the climatic consequences of that change were only beginning. Ice soon appeared across broad regions, revealing that the planet's atmosphere and temperature had become dangerously unstable. One likely mechanism involved methane, a powerful greenhouse gas that may have helped warm Earth beneath the faint young sun. As oxygen chemistry reduced atmospheric methane, part of that greenhouse protection may have weakened. Cold storms crossed dark oceans as ice began spreading across coastlines, once shaped only by waves and lava. During the Huronian glaciations, glaciers reached regions that geological evidence places surprisingly close to the equator. Great ice masses moved across the barren cratons, cutting valleys and carrying debris toward low-latitude seas. Earth may even have approached a near-global freeze, although the true extent and timing of the ice remain uncertain. Along frozen coasts, dark ocean, fractured sea ice, bare rock, and glaciers created a radically different planet. Volcanic carbon dioxide and other long-term feedbacks could eventually rebuild greenhouse warming and weaken the deep freeze. As ice retreated, wet basalt and mineral-rich meltwater reappeared, feeding fresh material into the ocean. Across millions of years, oxygen and climate may have oscillated through repeated advances, retreats, and environmental crises. Through every crisis, microbial communities persisted in protected shallows, sediments, deeper waters, and ice-free refuges. For strict anaerobes, however, oxygen was toxic, shrinking their habitable world into darker, oxygen-poor environments. Many survived below the surface, where layered sediments preserved chemical zones suited to ancient microbial metabolisms. But oxygen also made far more efficient energy-producing metabolism possible, opening biological opportunities that had never existed before. As oxygen accumulated, an ozone layer could begin forming high above, reducing harmful ultraviolet radiation at the surface. Complex life did not appear immediately. For more than 1 billion years, Earth remained overwhelmingly a microbial planet. Yet a permanent door had opened toward larger cells, more complex ecosystems, and eventually the first animals. Earth did not become habitable in a single moment. Its transformation unfolded through chemistry, climate, catastrophe, and survival. Microbes changed the planet slowly until the oceans recorded their work in iron, and the whole world began to rust.